In Practical 5, our aim was to construct an electromyography circuit that would utilize minute muscular depolarization in a person's muscle to drive a lead. Nerve cells, called motor neurons, transmit electrical signals that cause muscles to contract and relax. To translate these signals, an electromyography, or an EMG, is performed. EMG is a diagnostic procedure that appraises the health condition of muscles and their motor neurons. Therefore, EMG is an effective way to detect a muscle or a nerve disorder. Now, to detect EMG signals, we want to build a differential amplifier with high CMRR to reject all the signals. We set up a pre-amplification circuit and connected two electrodes on the muscle being examined, approximately 1 cm apart, and a third electrode, the reference one connected to ground, placed on the elbow. That way, the voltage difference between the 2 points could be observed. But fixing the electrodes directly to the differential amplifier would draw too much current from the electrodes and the voltage would drop to almost zero. So, to our rescue, a wild instrumentation amplifier appeared and a higher power signal was created. Here you can see a drawn picture of the final circuit that shows all the connections. The calculations here show how we chose different values of resistors but kept the same capacitor. That made the circuit and measurement a lot easier to experiment with. Because we're all different, thickness of skin, dryness of skin, muscle size and such things, the gain resistance had to be calculated for each person and each muscle group. The higher the gain, the lower the resistance is. With our MCP6004, we sampled a second-order bandpass by combining a second-order high-pass and low-pass filter. Because of Europe's metric standards, we want to have our cutoff frequency between 60 and 500 Hz. Now, after calculating different values for capacitors and resistors, we try it out and find out which frequency between 60 and 500 Hz fits best for each individual. We used 100 nanofards. We did 3 different measurements. Since the lab didn't have all the resistors that were calculated, we used the ones who were closest to the right value. The frequency range was the same for all group members, but the gain varied. Let's start by looking at Rannveig. The bicep is a two-headed muscle between the shoulder and the elbow. 2 electrodes were placed on the surface above the muscle and 1 on the elbow as said before. By mistake, we first examined Rannveig's bicep with no filter, since both the high-pass and low-pass filters were 60 Hz. The circuit therefore contained 4 27k ohm resistors, 4 100 nanofarad capacitors and a gain equal to 10, even though, surprisingly, it worked in the very first try, which is not common. Then we fixed our circuit and took a better look at our filters. The frequency range was set between 60 and 500 Hz. The first filter, the high pass, was kept at 60, but the second filter, the low pass, was set up to 500. Therefore, the high pass filter contained 2 27k ohm resistors and 2 100 nanofarad capacitors. The low pass filter contained 2 3.3k ohm resistors. The gain was still equal to 10. This worked well and gave a clear response. When Rannveig contracted the bicep, the LED was blinking, but when she relaxed and stretched out her arm, the LED went off. It's amusing to think about what would have happened if her bicep would have reached tetanus state. Perhaps the LED would blink very fast and then be fully on before going off. For Gudrun, we placed 2 electrodes over the calf muscles and 1 on the ankle flexors. We didn't get any response at first, and we thought that was because we need to increase the gain over the resistor, but that wasn't the only thing we needed to think about. Gudrun wasn't grounded. She just sat in a chair while we were trying to figure this out. But when she stood up and placed her foot on the floor, we got some response. So after trying out different values of resistors and gains, we ended up with the same frequency as in Rannveig's measurements, but the gain was set to 100. We also experimented with positive and negative supply voltage. The negative supply was set around 7 to 8 volts, while the positive supply was set to 12 volts. Gudrun stood with weight distributed equally between both legs, looking directly ahead. Then she sways forward from the ankle slightly, and to get the most muscular tightness, she stands on her toes and then relaxes. The LED was blinking a bit, which indicates that the muscle is constantly contracting, just as in the bicep. The final result was that the best possible output was when the frequency range was set between 60 and 500 Hz, and the gain at 100. That is a 500 ohm resistor. The high-pass filter was kept at 60 Hz, but the low-pass filter was set up to 500. For Inga, we chose a back muscle called latissimus dorsi. We placed 2 of the electrodes on either side of the center line of the back, and the ground was on the elbow. Then Inga stood up from a chair and we got a clear response on the LED, and also if she sat down on the chair and tensed the muscle. The output of the LED is on when a high flow goes through it and the muscle is contracted, but off when a low flow goes through it and a muscle is at rest. The brighter the light is, the better response and more muscle contraction is happening. The reason why Inga and Guðrún both had a good output when the game was set to 100 with Rannveig when her game was set only to 10 is probably due to the muscle type and size. Both the calf and the back muscles are rather big, but the bicep is a lot smaller and more sensitive.